Okay, this is talking about universal gravitation, lesson 4.2 for physics 20. Now, first thing that we're going to take a look at is Galileo observed that all objects fall with the same acceleration. Now, combined with Newton's law of motion, F equals ma, that means that the force has to increase proportional to the two masses between the objects, right? If you've got, let's say, mass 1 and mass 2 here, if this is accelerating at 3.0 meters per second squared, and we've got a different mass, let's call it mass 3, with this mass, and it's also accelerating at 3.0 meters per second squared. Let's just pretend that's the Earth. So you got mass, one mass falling. Oh, I should put this at 9.8, if I've got that in the Earth. So, accelerating 9.8, 9.8 down, both, but because they're different masses, the one that's bigger must have a bigger force in order to keep that, must have a bigger force with that bigger mass in order for this acceleration to stay the same. So what we say is that force is proportional to m1, m2. That's not the only factor, but it is one of the factors. Now, Newton also realized very early on that only an inverse square law for the dependence of gravity on distance would work, given Kepler's laws of planetary motion. So taking a look at laws of motion in the heavens and whatnot, found that a force of gravitational force had to be proportional to 1 over the distance squared. So if you double the distance, you have 1/4 the gravity, not just half the gravity. Now when we put these two laws together, you wind up with it's proportional to m1, m2 over r squared. But in order to make all the units and work everything else, we need this g. You need to figure out what g is. It's a proportionality constant. And in your book, you'll notice that, or formula sheet, you'll notice that that is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Now, really, this is just a tie-in for our relation between what we've defined as a Newton of force and what we've defined as a kilogram of mass and what we've defined as a meter of distance. Right? So it's a number based on all the definitions we've got for these things, just so that everything makes sense. And we call that a proportionality constant, Newton's gravitational constant. This number will always be 6.67 times 10 to the negative 11, no matter where it is in the universe. It is universal. Right? So in simpler terms, the force, the attractive force between two masses, here we've got mass, is proportional to the multiplication of the masses divided by r squared, and it's known as a universal because anything with mass will attract anything else with mass. Right? So gravitational force between two masses, m and m, is proportional to the product of their masses and inversely proportional to the square of the distance between them. So everything in the universe attracts everything else. The Earth is attracted to the moon is attracted to the Earth, and this guy realizes that that girl is going to be attracted to him gravitationally. But of course, compared to the Earth, the masses are actually quite small. So she points this out to him, saying that because the masses are very small by comparison, the gravitational attraction is also going to be very weak. So the guy eats and eats and eats, and gets really fat, and he says, "Any stronger now?" And the girl says, "Well, it's not measurably different. Even though you weigh 50 kilos more, reality is it's not very different." That number g in the formula is a constant of nature, indicates how strong the gravitational force is. We would need to perform an experiment to measure the exact attraction between two known masses at two exact distances. Now, this happened about 100 years after Newton's law of gravitation was discovered. And I've got a spelling mistake there. Henry Cavendish proved Newton's theory was correct, and he took two masses, large masses, two smaller masses around a really fine wire. And so you could know this distance, and you could measure the acceleration as this moved between them. And that acceleration, of course, was a force that was doubled due to the fact that you have this happening in both ways. Found G to be 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared, and this is a value that has been identified repeatedly again and again. So looking closer, it states that the gravitational force is directly proportional to two masses, right? Fg, m1, m2. The gravitational force between two masses varies inversely to the square of the distance between the centers. Fg is equal to something over r squared. And if the two masses and distance are known, we can calculate the gravitational force between them because we now have G. Again, G was discovered about 100 years after the proportions were discovered. So, taking a look, in one experiment, two spheres, one with a mass of 1 kilogram, the other with a mass of 1,000 kilograms, are separated by a tiny force if they're separated by 1 meter. If the spheres are replaced by a mass of 3 kilograms and 2,000 kilograms, still 1 meter apart, what is the relation to the force? Give it your best guess. Pause the video if you need to. Welcome back, and you should have found that this is 6 times the amount, D, because the 1 kilogram was replaced with 3 kilograms, that means 3 times the force. The 1,000 with the 2,000, that means 2 times the force, for a total of 6 times the force of that first experiment. So, if we were to calculate the gravitational force on a 600 kilogram spacecraft, that is 1.6 times 10 to the 4 kilometers above the Earth, we're going to start off with our formula. We plug in the numbers here. G, we know. Mass of the Earth, we get that from our formula sheet. This was given in the problem. Now the distance, we've taken the distance above the Earth in meters, 1.6 times 10 to the 4 converted to meters, and we need to also add the radius of the Earth because it's between the distances. So if we've got spacecraft here, Earth here, we're looking at this distance as being r. So we have to add this distance of the Earth, winding up with a 480 Newton answer, or 4.8 times 10 to the 2 to 2 significant digits. So what happens if we've got two 50 kilogram masses? We know that it's a force of 2.96 times 10 to the negative 7 newtons. How far apart are the objects? Well, again, we're going to run through this formula, but we're looking for r in this case. So we're going to need to manipulate to solve for r. Now, we'll square root at the end here, but we'll plug in our numbers, 6.67 times 10 to the negative 11. And we got two masses of 50. Now, you could put 50 squared or just 50. Either way is fine. I'm just going to put 50 and 50. And the force of 2.96 times 10 to the negative 7 meters, newtons, sorry. And so that radius, that distance between the centers, is 0.56 meters squared. And so r is the square root of that 0.75 meters in distance. So they are 75 centimeters apart. You've got 50 kilograms, and that's 75 centimeters, or 0.75 meters apart from their centers. And the reason for that, if you think about the two objects, we use the centers because the distance between here and here is a little bit less, the distance between here and here is a little bit more, and we use the centers just to get kind of like the average of all that force. Okay, I do hope it helps. If you do have any questions, please let me know, and thanks for watching. Oh, sorry. One last thing. G, what is G? Universal constant, 6.67 times 10 to the negative 11 newtons kilogram meter squared per kilogram squared. How do we calculate the force between them? We're going to use the G m1 m2 over r squared formula. It is mass that causes that attraction, the attraction between masses. And it is important to note that this is always an attraction force. And they extend, well, really forever. Although you do get to a point where that r squared, no matter, it gets so big that this force is going to get very, very small. But they do, in fact, extend forever. I do hope that helps. Thank you for watching. Have a great day. Bye.